All right, so we're back again, and let's just turn down the music a little. So we're thinking about this idea that maybe if our group is not cyclic and all, if we're able to show that there's some element of order p to the alpha times L, then if we prove that, it appears that that solves our problem. But the challenge still remains: how do we show that there's an element of order p to the alpha times L, where L is some divisor of M in the group, right? So our idea was, maybe let's do contradiction. Let's contradict this statement that there is some little g in the group G such that the order of G equals to p to the alpha times L, right? How do we contradict it? If there is no element whose order is p to the alpha times L, and we're saying that for all little g in G, right, for all little g in G, order of G equals to p to the I times L, where I is strictly less than, right? Isn't that what we're saying? I is strictly less than alpha, right? And we're saying that the order of every element there must be of the form p to the I times L, but I must be less than alpha, because isn't it true that if the order of G must divide p to the alpha times, if the order of little g must divide p to the alpha times m, the order of the group, doesn't that mean that every element is of the form p to the I times L? Okay, anyways, let's now go back to, so what we're doing now is just exploring, well, what are the consequences of saying that there is no element of order p to the alpha, right? What's the consequence of saying that there is that? What are the consequences of saying that for all g in G, there is no, for all little g in G, there is order of little g never equals to p to the alpha? That's what we're exploring here. What are the consequences of that, right? And the idea we seem to have come to before, at least, was this: that we can create a set of all the possible orders of elements of G. And we're saying that, first of all, since we already know, let's see, don't we already know that the order of every element in the group is of the form p to the I times L? Okay. Now the only question is, well, what are the powers of I and L? If order of little g can never equals to p to the alpha times L, and we're saying that uh, in that case, whatever the order of little g has to be, it has to be less than p to the alpha times L. But what does it mean to be of the form p to the I times L, but still be less than p to the alpha times m, right? Doesn't that mean that, well, either I is less than alpha, or L is less than m? Okay, there's no exclusive stuff here, actually, right? Or L is less than m, right? So it could be the case that I is less than alpha and L equals to m, or just L is less than m and I is equal to alpha. Actually, if we had, we're saying that, ooh, aren't we saying more, right? Aren't we saying more here? We're saying that, okay. So yeah, let's make sure we're clear. Clarity will either help us to eliminate this option or use it somehow to solve the problem. So would you agree that B is the set of all possible orders that elements of G can have, right? In the power of I will have to either be less than alpha, or L would have to be less than m, right? And of course L is being taken to divide m. Okay, all right. Now what happens when L equals to m? Well, if L equals to m, right, well, doesn't that just mean that if we have some element where order of G equals to Well, actually, p to the I times m. Nobody said that can't work. Right. Okay, that's fine. But really what we're worried about is in case, well, okay, we already said I cannot equal to alpha. Okay. We're good. All right. So we have this set B. Question is, how can we use, right? Let's actually state a question. How can we use the set of all possible orders of elements of G in order to figure out that there must be an element whose order is p to the alpha times L? There must be, can we prove there's something inadequate about this list, is the question. Well, what would it mean to show that there's something inadequate about the set B of all possible orders? Of all possible orders of elements, right? Well, what would it mean to show that something is inadequate? Well, maybe let's just look at, well, how many elements are in it? Do we need to go that far? Before we think about, well, how many elements are in B, how is that going to help us to show that there's something wrong? There's a how is that going to give us a contradiction? All right, let's explore that for a while. Just if for no other reason than just to eliminate it. Let the set B be, as we saw before, the set of all p to the I times L, such that either I is less than alpha or L is less than m. Okay. Now, how many elements does this set B have? Well, can we say that the number of elements in the set B equals to alpha minus 1, right? That is, how many possible powers can P take, right? If we count all the possibilities, it could go from 0 to what? To alpha minus 1, right? So how many, this was alpha minus 1, okay. How many elements are there, how many possible values of I are there? They're alpha minus 1, so they're, can we say that the alpha minus 1 possible powers that P can take? Okay. And for each of those powers, how many possible values can L be? How many divisors are there of L? Well, that are potentially less. Wait. Before we even get there, let's proceed. Let's try and proceed maybe even more systematically than we are right now. Just think about this. This statement is an OR statement, right? Either I is less than alpha or L is less than M. Okay. Well, suppose uh, if it's an OR statement, it means that one can be true and the other one isn't, right? Can't we say that? So, for instance, is it possible for L to be less than M and I to be equal to alpha? Right. Well, if this is true, if L is less than M and I equals to alpha, well, yeah, well, what's wrong with that? Well, because we also have the other issue. Just because we have the set of all possible orders of elements of G doesn't mean that all those orders are actually used up. Here's why. Or at least it's 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 not necessarily true. Okay. Here's what we're saying. Lagrange's theorem tells us, right, that if G is a group, then order of every element little g of the group must divide the group. Right. However, does it tell us that if some number divides G, then there must be an element of the group G whose order equals to that divisor, right? So we don't know that. Like, one direction, sure. If G is a finite group, then order of G must divide the group, must divide the order of the group. Fine. But is it true that if some number divides the order of the group, then there is some element of the group whose order equals to that number, right? So we're not sure of that statement. And if we're not sure of it, either we prove it or we just can't use it, right? So we don't know this yet. So perhaps it's not the path to go. So, but why did we bring it up? So the reason we bring it up is that it's possible for there to be some p to the I times L. It's possible that for some j and k, that p to the j times k is actually an element of B. That is, p to the j times k is actually a divisor of p to the alpha times m, but at the same time, however, p to the j, there's actually no element such that p to the j times k, there's not, it's possible for us to have some p to the j times k element of B, right? But where perhaps for some, there does not exist g and g, little g and g, such that order of g equals to p to the j times k. Another way of stating this is, perhaps we can have some potential order of an element in B, when in fact there is no element in G which has that order, right? So just because something is in B does not necessarily mean that that thing, there's an element of the group whose order equals to it, is what we're saying. So, but what can we learn about this collection before we even think about if the collection is going to be helpful to us or not? The collection B. Okay, or maybe rephrase, different question. Is there something that has to be true about B, such that if it were violated, something would it would mean that something's wrong with some assumption we've made? That is there anything that has to be true about B? Right? Even if we know that every element of B is not necessarily going to correspond to, there's not necessarily going to be an element whose order gives us that element of B, but is there something that always has to be true about B? Right. Is a question. Well, one thing, can B be empty? Right. Can B equals to the empty set? Right. If P is actually, we said P is a prime, right? And we're looking at P to the alpha times M. P is some positive, P is a prime, so it's obviously, can we say it's positive? And M, we were saying M is not equal to 1, it's something greater than 1. So, is it possible for P to the alpha times M to have no divisors? Right. So, if we're saying that B can't be empty, okay. So, alright, so maybe that's something we can contradict, that maybe the assumptions we're making would lead us to say that B is empty. Perhaps. Well, let's say the way we've defined B, right? Are there certain elements that it cannot contain? For instance, can P to the alpha times M be an element of B? Is the question. Right? What would that mean? Well, right, so question, can P to the alpha times M be in B? Didn't we say that B has the elements where the power of P is less than alpha? Okay. So maybe the power of P is equal to, maybe the power of I, maybe I equals to alpha, but if I equals to alpha, then we're saying, also, aren't we saying that the first condition is not true, that I is less than alpha? So doesn't that mean that L has to be less than M? But if L also equals to M, don't we have a problem here? So again, we ask the question, can the element p to the alpha times M be in B, right? All right. Given that, well, first of all, we have that the first condition is not satisfied, right? I is actually equal to alpha, and L equals to M, so can P to the alpha times M ever be an element of B? All right. If we're saying that, if we say that P to the alpha times M is not an element of B, okay, so maybe that's another piece of information we can use. Perhaps a contradiction we can come to is saying that B contains the element P to the alpha times M. What else? What else has to be true about our collection of our collection B, our set B? Right? Suppose we define a different set, that is a set C, which allows us the powers of alpha. That is, the set C equals the set of all P to the I times L, such that I is less than or equal to alpha, and or L is less than or equal to M. So this one is a little different, isn't it? Because aren't we allowing I to be alpha and aren't we allowing L to be M? So can we at least say that B has to be less than the order of B has to be less than C? That is, alright, we just ran out of time, so we'll continue studying this set B, the set of all possible orders of elements of G, and see if that could give us an approach here, and maybe we can use this information to show us that no matter how hard we try, we'll always find an element of the group whose order is P to the alpha times L. And if we do this, it appears that we're done, because won't we have shown that if a group is not cyclic, we have an element of order P to the alpha, and did we prove before that if a group is cyclic, then is cyclic, we also have an element of order P to the alpha, right? So perhaps this may enable us to complete Sylow's theorem, a study of this set of all possible, the set of all possible divisors of P to the alpha times M. In this case, proper divisors that seem to exclude the element P to the alpha times L, the element P to the alpha times M. Anyways, so please do think about it. See if studying this set B could somehow help us to resolve this Sylow's theorem. It's getting very convoluted, but that's the beauty of exploration, right? Is we never know what we'll find. We could find alligators, we could find dangerous animals, coyotes, beasts, and we had the adventurer adventures anyway, you know. Sometimes he finds something, sometimes he doesn't. But that's the beauty of the adventure, not knowing. And right now we are steeped in ignorance. We're studying a set and we don't know if it will work. We don't know if this approach is the right approach. And if this approach doesn't work, well, what approaches are we going to try? It's all mystery. And that's actually what makes it beautiful. Alright, thank you very much for watching this video before we descend into philosophy. But yeah, have a relentless week. Bye.